So, hello everyone, and welcome to the first lecture of our course, Reliable Simulation in the Mechanics of Materials and Structures. Today we will have a short introduction and overview and some definitions related to our course. So let's start with some general information. We have lectures on weekly basis. So every week on Monday from 10:30 to 12, I will be online via Zoom. And I will upload before the lecture some videos which will be considered as supplementary videos to the lecture. And we have also the exercises. They will be also on Mondays, also between 16:30 and 18. They will be given by my colleague Hassan Swaidan. And we will also use the RWTH model, so you will find there links to Zoom meeting. Also, I will upload all of the lecture notes, the videos. We can have also discussions. You can also ask questions through RWTH model. So it's a great platform. We'll have this year also homework assignments as we did last year. These are connected with bonus points. So if you succeed in the homework assignments and you succeed in your final examination, then you can improve your grade. For instance, if you succeed with a grade of 2.3, then your final grade will be exactly 2. And we are planning to have written examination. So because we usually have a large number of participants in this course. Let me start by giving an overview. So today I will discuss the first section, so the overview, definitions, and introduction. And then from next week we will start with the second section, where I give a short introduction to mechanics of materials and structures within Continuum Mechanics. So you'll find some information are somehow could be found in other courses, but here we address these issues in the context of reliable model. Then we will talk in the third section about the conversions within finite element analysis, some issues like the H and B mesh refinement, the mesh conversions, how to quantify the conversions. And then in the fourth section, we will have some time-dependent problems. So we'll talk about the how you model this and how you apply like time integrations and what could be the challenges, where can you apply a certain method and where you are preferred not to apply a second method and so on. Then a considerable part of our course will be about coupled problems. And here we will start by some definitions, and then we'll talk a little bit about the structure of the governing equations. And we'll have also two examples. One is related to thermoelasticity, and one is related to fluid structure interactions. And in the last section, I usually address some new trends in the field of computational mechanics. This year, I will talk a little bit about the implementation or the embedding of artificial neural networks in the context of computational mechanics. I will show you some new results and some recent research in this context from our group. So let's talk a little bit about the related literature. There are a lot of books which address topics of this course. I can recommend a lot of these, and here I have 5 as for example. I always recommend you to go to the literature or the internet, and then just to get maybe deeper inside the topic, and then you understand it also from different point of view. I'll try, however, in the lecture to explain everything. So most of you maybe don't need to go to the literature, but I recommend this. And I will mention throughout the course some additional literature. Maybe I will also upload some papers which you can use also to deeply understand this. So let's start with the real material. Now, reliable engineering simulation. So the simulation in engineering applications in mechanical or civil engineering is a very important topic nowadays. It was not the case like years ago, like 30, 40 years, the simulation results were not considered that much reliable. So they did not use it in the certification or in the design. Nowadays, they are a very important part of the design, the qualification and certification of certain products. And the acceptance of numerical simulation and also the virtual testing, it adds a big responsibility to engineers, because now they can, this numerical data and results can be used directly in building a new product. And this is a big responsibility. Through verification and validation of a model, then you can prove, or you can like defend your model, and you can say, okay, my model is reliable because I have this verification process and I have this validation data. So the issue is something similar to shooting an arrow to a target, and your model, if it's reliable, then it will hit the target in the yellow spot. And reliable means here it's accurate, it's stable, it's not so complicated model, and it's also computationally efficient. And remember, your model can be used in a direct product like design of airplane or a car. So there are a lot of responsibility. That's why like deep understanding of like valid and reliable model is very important topic. So what are the stages of model development? So I show in this sketch like the significant steps in the design of a reliable model. So we start as usual from the real problem. So let's say our real problem is this board, and then we have this lady, she's jumping in water, and you are, as engineer, you are asked to design this board so that it's not broken. Then we have the conceptual model, so you replace the board by some kind of beam, and then you have to give some assumptions about the supports and of course the load and so on. And then we have the mathematical model, so how I can describe maybe the stresses or the loads inside this board. So there are like several approaches. For instance, this board is a beam, so we can follow the beam theory. There are here a lot of assumptions, so we can also have this. And we could also model the beam as a continuum material, so within continuum mechanics. Both beam theory and continuum mechanics, they will give us some equations, and then we need to solve these equations. And this is a numerical treatment or analytical solution. For beam theory, it might be possible to go for analytical solution. For continuum mechanics, it would be very much complicated, so we'll go for numerical treatment. And for this board, for instance, we can also apply some experiment. Once we have the experimental data, the numerical data, and the analytical solution, then we can apply the verification and the calibration. So let me just give you these definitions precisely. So the verification is the process of determining that a computational model is accurately representing the mathematical model. It means that the model is, it's accurately implemented, so the implementation is correct. It's stable, so you don't have like numerical oscillations. It means that you implemented this model correctly. And then we have the validation. In the validation, we compare between the numerical data and the experimental data. So we compare this with the reality. If this conversion led to a good agreement, it means that our model can, to good accuracy, represent the real world, and then our model would be valid. And as a part of validation process is the calibration. So the numerical model includes some parameters which have to be tuned with reference to the experimental data. So this process is called the calibration. So we are adjusting the material parameters so that the model fits well with the reality. Let's take an example. So we talked about the board. Now we will talk about the aircraft wings. So you have this physical system, an airplane, and we are addressing the deflection in aircraft wings. And for this, as an engineer, you are asked to develop a reliable computational model to compute the wing deflection under distributed loading. So let's say, under self-weight. So the airplane is not flying, it's on board. And we want to know how much deformation or deflections happen in the wings. We have additionally experimental data. So we build like wings in the laboratory with a lot of sensors to measure the deflection, and we apply the self-weight as load and so on. So we have, let's say, reliable experimental data. So this is the real model, and then we have the conceptual model. It's, as we said, it's constructed based on the collection of assumptions and descriptions of the real system. In this case, the airplane wings can be approximated by a cantilever beam, which is like clamped from one side and it's free from the other side. And the self-weight will be replaced then by uniform loading. Let's call this Q3. We can also like apply some additional assumptions, like we say that the deformations in the wings are small, and the behavior or the material behavior is elastic. So this wing will not be broken due to self-weight, of course not. And then we have also elastic, so it will not also. There are no creep or relaxation, so we have no time-dependent behavior. So this is the conceptual model. And then we come to the mathematical model. So how can we describe, let's say, the deflection in these wings? So the mathematical model includes, for instance, the kinematics, which is a relationship between the strain and the deformation, the constitutive model, which is a relationship between the stress and the strain, and also the governing equations. For instance, here we have purely mechanical problems, so we can take, for instance, the linear momentum balance, and we could have additional assumptions. So as we said, in mathematical models, there are several approaches. So if we go for like the beam theory, we can take, for instance, the Bernoulli-Euler beam theory. So this sketch shows you how the beam look like with its distributed load. And the deflection can be described with this one equation. It's also coming from the linear momentum balance. It's a differential equation of fourth order, so we need to integrate this like 4 times. And in this equation, we have this W is beam deflection, G22 is a moment of inertia, and E is elasticity module. We have an assumption here as a constant bending stiffness, so to make things simpler. There are also in the literature several ways to solve this this equation, and this can be also learned in the context of fundamentals of mechanics here in your study. But we can make use of the boundary conditions also to solve this equation analytically. The boundary conditions, for instance, on the left-hand side, we have fixed boundary. It means we have no deflection, and the first derivation for this clamp is also 0. On the right-hand side, we have a free boundary. So this, the second and third derivation of the deflection is both are zeros. So for the analytical solution, which is somehow relatively easy to implement, we propose a solution of this form. So W would be include a sine and exponential function. And you see in this equation, we have A, B, C, and alpha as constants, which are unknowns. Now, if we take the first, second, third, and fourth derivation, then we have four equations with 4 unknowns, and with the help of the boundary conditions, we can determine A, B, C, and alpha, so that we can also construct our solution. This is one possibility. And if you want to go to another approach, for instance, the continuum mechanics, then you can describe the material behavior at each material point. For this would be the kinematics, which is the relationship between the strain and the deformation. And here I'm choosing a simple expression, which is a linear strain tensor. And then we have the constitutive relation. It's between the stress and the strain. And we have C4, which is the elasticity tensor. And we have also the balance relations, as I mentioned before. It's the linear momentum balance. We call this local form because at each material point of our continuum material, these balance equations should be true. It means that we are now talking about material points. It means we need to integrate these equations over the domain to solve this problem. So analytical solution would be possible in space. So if we have like very simple geometry, or if we have one-dimensional case. However, it's almost impossible for a real problem to go for analytical solution. Sometimes we apply analytical solution just to verify our code for simple cases. But for real problem, we have to go for numerical solution, and this leads us to, for instance, to the finite element method. It means that for the finite element method, we are now moving to the numerical treatment. For the numerical treatment, I assume, or I'm sure that many of you are familiar with some packages like Abacus, like ANSYS, and in this course we will use another package, which is a FlexPDE. It's very user friendly, and there's a free student version of it. And if you apply your model in a finite element code, for instance, here in Abacus, you have to give as input the geometry, the material parameter. You have also to deal with the spatial and time discretization. So these are all topics which we will address in this course. And then you'll have the output data, which you have to post-process to see and your data, and then you compare it to the experiment. So when we have the numerical data and we have some analytical solution, then we can apply the verification. So as certain, the verification aims to assure that the numerical discretization solution is accurately implemented. As I said, it's related to the accuracy and also to the stability. But this is not always guaranteed. So sometimes we have some errors, and the source of these errors could be, for instance, the spatial discretization. So if you apply a very like coarse mesh or very fine mesh in some places, so you'll have some stability problem. Maybe the time discretization also plays a certain role. For instance, if you apply explicit time integration scheme, then you'll have some critical time step. So you'll have stability issues, then you have to change this. You have also some linearization error, because most of the time you will end up with nonlinear system of equations, which you have to linearize. This adds some errors due to numerical schemes for linearization, and this is also another source of problems. But remember, even if your model is verified, this does not mean that your model can be implemented for reality yet, because you did not compare the model with real scenarios. So verification is something, and then validation is another thing. So we still need to compare the model with real scenarios. And this leads us to the validation. The aim of the validation is to assure that a numerical solution represents the reality. If you have highly confidential experimental data, and by the way, experimental data require a lot of effort, and they cost a lot of money. And if you have this data and you are sure that they are correct, and you are aware of all the boundary and the initial conditions and the atmospheric issues around the experiment, and then you have observed big differences between the numerical and the experimental data, then you have to think about some issues like changing the conceptual model. It could be that cantilever beam for airplane wings is not the best model. Maybe you have to add some degree of freedom to one side, or the free end might be also adjusted so that we have a better conceptual model. Maybe you have to change the material model which we put in our numerical model. For instance, we started from the assumption of linear elastic. It might be that we need to change this to nonlinear elastic, could be. Maybe the material parameters which we have calibrated or adjusted during the conversion between numerical and experimental data were not accurately chosen. So maybe you have to rethink about this. there are some optimization strategies in order to select the parameters in a proper way, or we are currently testing some machine learning based approaches to figure out the best material parameters. So this leads us to what we call the application domain. So where can I apply my model to which kind of problems? So starting from the left, if the validation domain is big, it means I have a model which I have tested for many scenarios for linear, nonlinear, elastic, small and large deformations and so on. And I have a problem like the airplane wings, which has elastic and maybe small deformations. It means that all the loading and material behavior scenarios are already included in the validation domain of our model. So it means that we can apply our model to all these scenarios. Now, if my model, for instance, is tested for quasi-static and dynamic loading, but my structure in reality it's subjected sometimes to dynamic, sometimes to high frequency loading, so that dynamic loading with high frequency, so that my model cannot capture that scenario. It means I can apply my model only to special cases of dynamic loading, but not for high frequency. So I have like overlapping, but it's not all the scenarios are included. Or maybe I cannot apply my model at all to some real application, like my model is only designed for quasi-static case, and the structure is subjected only to dynamics, so I have no way to apply my model. So this is depending also on many issues, like for instance the material parameter. They could be, for instance, dependent on the temperature. So if it's not included in the model, then my model will not be good. In this case, as I said, loading conditions, safety factors. So if the accuracy is very high, is a very important issue, maybe my model is not accurate enough. Sometimes we have environmental factors. So if the model does not consider, for instance, the humidity or the temperature of the atmosphere. So if I'm designing a structure in, I don't know, in Norway, and this structure will be used in Australia where we have 50 degrees difference. So it means maybe the modeling is not really good for this kind of applications. So in this case, the experience of the engineers play a very important role in deciding which model can be applied to which scenario. So let's go back to this this overview. So we have, as I said, we have a real problem, as you see here, which could be like coupled or uncoupled. So we talked about the aircraft wings. It's an uncoupled problem. We have only the displacement as a variable. But we could also have coupled problems, as we will see in the course. The coupled problems will include, for instance, the thermoelasticity or fluid structure interaction. For the mathematical modeling, using the continuum mechanics, we will address in this course the kinematics and the balance equations, also constitutive equations for different kind of material response. And then we'll talk about the numerical treatment. Here we have is the finite element method. It has a lot of influence on the reliability of the model, how you implement it, and the sources of errors and the convergence. We have also considerable part related to time-dependent problems like viscoelasticity, and as I said, we'll talk about implicit and explicit schemes. Yeah, and as I said, we'll have a lot of examples, and also in the exercise, there will be finite element implementations in the software FlexBDE, which will also help you to deeply understand the topics. And I hope at the end also you will succeed in the course in a very good grades, so 1.0, hopefully all of you. So with this, I'm at the end of the first lecture. I hope we see each other in the Zoom meeting, and until then, I wish you a good day. Thank you.